Hi, everyone. We are back with some more office hours with Chegg. We are going over Organic Chemistry 1 every Tuesday at 5 p.m. PST. And so, yeah, go ahead and check out the QR code on the top left. If you want to see all the different topics that Chegg is offering office hours for. There's all kinds of math and other things. Right here, we will be focusing on Organic Chemistry 1. We've got the chat open, so if you want to ask some questions, I'll be happy to try to address them. Please keep them Organic Chemistry 1 oriented. You can ask a question based on the problems that I've brought to review with you guys, or you can feel free to ask something else, Organic Chemistry 1. That's not what I'm talking about. If it's something that I can address, I will do so. So let's go ahead and check this out. There's something's looking a little bit funny. I'm not sure why this is red. Can you guys? I don't know why is that showing up red there. If that's showing up red to everybody, maybe I will actually just really quick quit this and relaunch it. Hopefully it will show up better this time. Yeah, let me do that and share again. Let's make sure that pops up. Ooh, that is showing up red. I have no idea why that looks that way. Let me just kind of correspond. Okay. Can just everybody in the chat, are you seeing this? Is this showing up normally for you guys? Can everyone just let me know if you're seeing it as we tend to see everything? On my screen, it's just looking just like bold red and very difficult to read. So if I can just get confirmation from people in the chat that looks normal. Okay, if it looks normal to you guys, then that's fine with me. Okay, so let's go ahead and get started. Now, for a few weeks now, everybody has been asking me to look at some spectroscopy, and obviously that is a very big topic. So the first time Organic Chemistry 1 students are exposed to NMR, it's incredibly confusing. You see these spectra and it's just, what is this? What am I looking at? What's going on? So let's do a really quick introduction to NMR. I'm going to give you just the very basics of how you're going to interpret an NMR spectrum. So when we're looking at an NMR, a proton NMR spectrum. So this is H1, right? We're talking about protium nuclei are forming are generating this data, these resonances. And so there's three things that we're looking at on the NMR spectrum. So we're talking about chemical shift. So that is the position on the horizontal axis of the spectrum. So ppm, right? We're looking at 1, 2, 3, 4, 5. To the left is downfield, to the right is upfield. So where the resonance sits on the horizontal axis, that is one bit of information there. Then number two, we're looking at integration. How tall is the peak? Or technically, we're talking about the area under the peak. It's exactly like integration from calculus, but just crudely speaking, how tall is the peak? That gives us some information. And then third, we're talking about splitting. So you have a resonance. How many smaller individual peaks is that resonance broken up into? So for example, so this is an overlay. This is this one blown up here. So right here at around 2 ppm, this is just this right there, right? And it's just blown up so we can see the splitting pattern. This is a doublet because it's two smaller peaks. And then over here, we have a quadruplet, okay? And so that is some other information. So chemical shift, where it is on the x-axis, integration, how tall it is, and splitting pattern. How many smaller peaks is it broken up into? So that's the information that we're going to be looking at here. And what we need to understand is that we have sets of chemically equivalent protons and chemically equivalent protons, which are typically the protons on the same carbon. Sometimes protons on the same carbon will be inequivalent, but usually, and certainly for these examples, they are equivalent. Those will contribute to a particular resonance that will be integrated to however many protons they are. So if one proton is generating a resonance, it'll be integrated to one. If two, two, three, three, etc. So the taller the peak, the larger the peak, the more protons are going towards generating that resonance. For chemical shift, we're talking about how close those protons are to an electronegative group. So electronegative groups like halogens and oxygen atoms are de-shielding. So they withdraw electron density towards themselves. So they're withdrawing electron density away from the nuclei of those hydrogen atoms, of those protons. And that is a de-shielding effect. And that causes that resonance to show up further downfield. So the closer the groups, the closer the protons are to the electronegative element, the farther to the left they're going to show up on the spectrum. And then finally, the splitting pattern has to do with neighboring protons. So however many protons are on carbons next to the protons in question, you add those up and plus one. It's the n+1 rule. So for doublets, if you have a doublet, that means those protons are adjacent to one proton, because 1 + 1 is 2. If you have a quadruplet, it means that those protons are adjacent to 3 protons, because 3 + 1 is 4, quadruplet. So those are the 3 things that we need to examine the most simple NMR spectra. And this is just the ground floor, right? Once you get this, then the rest is just additional rules on top. But this is all you need to go from the total confusion of what the heck am I looking at to just a very general, like, okay, I think I kind of understand this. So we want to understand which alkyl chloride matches this NMR spectrum. So what we can do is we can show all of the protons on these compounds, and we can make predictions about what kind of a spectrum we ought to see. So for example, here we've got 2 implied protons, we've got 2 implied hydrogens here, and we've got 2 implied hydrogens here. So how many resonances would we expect to find? Where are the chemically equivalent protons? Well, due to the symmetry of this molecule, these ones, all 4 of those are one resonance, and then these 2 are another one. So we would expect to see 2 peaks. These ones would be split into a triplet because these protons are all adjacent to a carbon with 2 protons on it. So what it is this hydrogen right here, we sees 2 protons next door. So n is 2, n+1 is 3. So the resonance would be split into a triplet. And then this proton sees the same thing, so that it's integrated higher. This proton sees the same thing, so it's integrated higher. This proton sees the same thing, so it's integrated higher. So we would expect to see a triplet that is integrated to 4. So we would expect to see, let's call this a 3H triplet. And then over here, we would expect to see a quintet, or honestly, around splitting into 5 or more peaks. We start to just call it a multiplet, and we would expect to have that integrated to 2. And so we're going to have a 2H multiplet. Okay. And which one would we expect to be more downfield? The one that is closer to the de-shielding group, the more electronegative group. So these protons are closer to a chlorine atom, to different chlorine atoms, but still they're adjacent to a chlorine atom. So that is going to be more downfield, and then this one is going to be more upfield. Okay, so that is what we would expect to see. Multiplet upfield, triplet downfield. So that doesn't seem like it matches too well, but let's keep going. Let's see what else we have here. So what about this one? We've got 1, 2, 3 protons on that methyl, and then right here we have just 1 implied hydrogen, right? So what are the groups? Well, obviously it's just going to be these 3 will be 1, and then this guy will be a different resonance. Now, what will we expect to see? So these guys will be integrated to 3 because there's 3 of them, and it will create a doublet, right? Because they see 1 proton next door. 1 + 1 is 2, doublet. So integrate to 3H and doublet. Okay. And so we'll talk about the chemical shift in a second. This one, we will expect a quartet. because we've got 3 next door. And so 3 plus 1 is 4, quartet, and it'll be integrated to 1. So we have a 1H quartet. And which one will be the furthest, the one that's further downfield? That will be this one here, because it's right immediately adjacent. It's on the same carbon that is bound to these 2 chlorines, not 1, but 2. So it's actually going to be quite de-shielded. So that will be downfield, and then this one will be more upfield. Now I'm just putting D and U. I'm just saying that one is more downfield and one is more upfield. I'm just comparing those two. That's all I'm doing with that. Okay, so now let's check this out. We've got H, H, H. We've got H, H, H. And then we've got just one implied hydrogen right there. So here, all of these methyl protons are equivalent, right? And then just this, oops, just this one proton will be the second one. And so here we'll have 6. This one is integrated to 6, and it'll be a doublet. So that's a 6H doublet. And then this one will be it'll be a messy multiplet, right? It'll be split into many, many peaks, because this proton sees 6 protons next door. 6 plus 1 is 7. So about 7 tiny peaks, and it'll be integrated to 1. So a 1H multiplet. And this one will be more downfield, and this one will be more upfield, because this one is immediately adjacent to the chlorine atom. So that's that one. And then lastly, we have H, H, H. Sorry, it's getting a little crowded there. We've got 3 protons there. We've got 1 proton there. We've got 2 protons there. We've got 3 protons here. Now, these will all be different, actually. So we've got this methyl here. We've got this individual one there. We've got these 2 here. And we've got these 3 here. So this is the only one that, even just by looking at the number of peaks, we know it doesn't work. This one would have 4 peaks. There's 2 peaks there. We don't even have to go over the splitting and all that stuff. We know that this is definitely not the case. The other ones all have 2 peaks. So now we have to compare the predictions we just made to the data that we have here. So first we have a doublet, and we have a quartet. So, well, that already is going to tell us that it's probably this one here. Let's make sure that the integration and the chemical shift also match, though, right? Because what we're doing is we're building a case for the identification, the characterization of this molecule, right? All of the data must agree. So if you have splitting, that looks good, great. Chemical shift, that looks good, awesome. Integration, that also looks good. If all of that data agree, then that is a very strong case for that being the right structure for the molecule. So the splitting pattern looks good. Let's look at chemical shift. We're seeing that the doublet is more upfield and the quartet is more downfield. Well, that looks good, right? The quartet is more downfield and the doublet is more upfield. That looks good. And then how about the integration? The quartet is integrated to 1 and the doublet is integrated to 3. So the doublet should be much bigger, should be a bigger peak. And it is, right? The doublet is much bigger. This is a smaller peak. So that all looks good. And definitely this is going to be the right one. So this is the this is the structure. It got a little crowded over there. So that's it, right? And so once again, hopefully, if you were very, very confused by even just the first step of how to look at an NMR spectrum, once again, this is it, right? We're looking at chemical shift, integration, and splitting pattern. Those are the 3 things that you're going to do to identify, to correlate a particular organic molecule to a spectrum. And this is sufficient for organic chemistry 1, right? It's not going to get to, it definitely gets much, much harder as you go further in chemistry, gets dramatically more complicated to interpret, but it's all based on these same principles, right? There's some other coupling constants and some other things that crop up, but this is kind of the basics here. So that's it for NMR. Let's see if we missed anything. Jordan asks if I can explain optical activity at some point. So just very, very briefly, optical something that is optically active is chiral. So if it is chiral, it is optically active. So if a molecule is chiral, it has an enantiomer, it is optically active. That means it rotates plane polarized light. So if you have a racemic mixture is not optically active because plane polarized light will pass through the sample. Half of the molecules will be rotating it one direction, the other half will be rotating it the other direction because they're mirror images. So the net effect is that there's no rotation of plane polarized light. So that sample is not optically active. It's also not optically active if it's not chiral. So if something is not chiral, it won't rotate plane polarized light. It won't be optically active. Or if it is chiral, but it exists as a racemic mixture, then it will be not optically active. If instead it is chiral and it is enantiomerically pure, then it will be optically active and it will rotate plane polarized light to some extent. And we can use that angle to make assessments about the optical purity of a sample. If we know that an optically pure sample will rotate plane polarized light clockwise 60 degrees or whatever it is, and the optical activity of a sample is 40 degrees or something like that, that's information that we can use to tell us about the distribution of isomers in there. We can tell that it's more of one isomer than the other. It's not a racemic mixture, but it's not enantiomerically pure. Otherwise, it would be all the way to 60. So a little less means some of the other enantiomers in there. So that's just really briefly what optical activity means. Thanks all you guys for letting me know it's normal. It still looks weird on my end. I don't know why that is, but as long as you guys see it, that is fine. Yeah, no, not Strand asks, how do I determine chiral centers in a molecule? So chiral centers in a molecule, we're just looking at carbon atoms that have 4 different groups attached to them. So for example, this right here is a chiral center because that carbon has CH3, CH2CH3, OH, and H. 4 different groups. It's a chiral center. And if a molecule has only one chiral center, it is certainly a chiral molecule. Okay. Let's see. Oh, Jofi says, can we look into pKa and pH and pOH? So that's really Gen Chem material. So we tend not to focus too much on that. But yeah, I mean, pKa, we can talk about like the pKa of individual protons on a compound. So the lower the pKa, the more acidic a proton, and the more likely it is to be extracted in an acid-base reaction. pH and pOH are the negative log of the hydronium concentration and hydroxide concentration, respectively. That's just telling you the acidity or basicity of a solution. So just really briefly, the one takeaway is that pKa corresponds to an individual molecule, and actually in particular, a particular proton on the molecule. Different protons on a molecule have different pKa's. And pH and pOH correspond with solutions, not molecules. So a molecule can't have a pH. A molecule has a pKa. A solution can't have a pKa. A solution has a pH or a pOH. So that's maybe the main, that's the key distinction there. Val asks, how to identify what is a strong nucleophile and what's a strong base? I know they're related, but I don't know how or why. So yes, obviously basicity parallels nucleophilicity. So things that are good nucleophiles tend to be things that have formal negative charges, or at least lone pairs. And those are things that can pick up a proton in an acid-base reaction. So there's different reasons why something might be a better nucleophile than a base. For example, if you're looking at oxyanions, or if you're looking at O minus versus S minus, S minus is still a very good nucleophile because it has a formal negative charge, but it's not a very strong base because it's so much bigger than O minus. It's one down. It's an analog. It's one down in the group of the chalcogens. And so because it's so much bigger, the negative charge is more stabilized. It's diffused around a larger volume. So it's not as basic, but it remains a good nucleophile because it has a formal negative charge. So things like ionic radius, right? That's one factor that would start to nudge something more towards nucleophilic behavior than acting as a base. But in general, nucleophilicity parallels basicity. So that is true. Uh, Lesson notes, Danny asks about mass spectrum and IR spectrum. I do have an IR spectrum in this presentation, so we will get to that. Mass spectrum, I don't have one on here, but I'll try to remember that for next week. Jen, Jupiter, chair and boat. So chair and boat and half chair and a few others. Those are all different. Those are all different conformations of cyclohexane. So cyclohexane looks like this from the top-down view, but from the side view, the most energetically favorable conformation is the chair. And so the reason this is the most favorable conformation is because it allows number one, for all of the bonds, all of the carbons exhibit perfect tetrahedral geometry with 109.5 degree bonding angles, whereas other conformations tend to put some strain on it. And then second, all these are all staggered interactions. All of the carbons in the ring they have staggered conformations with respect to each other, as opposed to eclipsing conformations as they do in some other ones. So the chair is just the lowest energy conformation for cyclohexane. I have some questions on that, a bunch of those in the first 2, 3, 4 weeks of these. So if you go to my live tab and go a bit earlier, I do a bunch of stuff on cyclohexane chairs because those are super important. uh, bu- 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 bu. Hard to, yeah. I says, I think a pH is the number of hydrogen atoms in a given solution. Kind of. It's pH is the negative log of the hydronium concentration. So hydronium is H3O plus, and pH is the negative log of that. So it's a way of expressing hydronium concentration, which is kind of like proton concentration, just in numbers that are easier. So instead of 10 to the negative 6, it's just 6. So it's easier to express and talk about. Uh, and so, no, it's actually a wandering traveler. It's the opposite. A higher pH means a lower hydronium concentration because of the way that logs work. So, yeah, the lower the pH, the greater the hydronium concentration. Yeah, that's how pH works. Andrew asks, how do you determine if an ion is a better leaving group compared to another ion? So there would be a couple of different trends. Number one would be ionic radius. So the fluoro group, fluoride is a bad leaving group. Chloride is better. Bromide is even better. Iodo is even better because of the radius, right? As you go down the halogen group, you're adding shells. And so as they get bigger, right, when an iodo group leaves, it becomes the iodide ion. The iodide ion is very stable because it's so big, relatively speaking, compared to the other halogens. So it's a much larger volume. It can diffuse that negative charge. It can spread that negative charge around a greater volume. So it can very easily accommodate that. So the iodide ion is so stable that an iodo group is an excellent leaving group. It's also the same reason that hydroiodic acid is such an incredibly strong acid, because the iodide ion is so incredibly stable on its own. So that would be and then there are other things like if there's resonance involved, if a fragment leaves and then the charge can be distributed around by resonance. That is it. The mathematician, how do you determine that is the lowest energy? I assume you're talking about the chair conformation. So we're talking about chemical potential energy. So the more that you push like charges together, the higher that goes in potential energy. It's like taking two magnets of like charge and pushing them together, right? It takes energy to push them together. So you're supplying the energy, and that brings the system to a higher energy. If you let go of the magnets, they go like that, right? They push each other away. And as they're pushing each other away, that potential energy is being converted into kinetic energy of motion. So higher in potential energy, when you let go, they go like that. So the potential energy comes down, right? Same with molecules. That's what dictates molecular geometry. When you have a central atom and a bunch of groups sticking off, that they're spreading out as much as possible in three-dimensional space, because that's what brings it to the lowest potential energy, right? They all have electron clouds. Every atom has an electron cloud surrounding it. Those are all repelling each other, so they all spread out as much as possible. And then it's the same with cyclohexane chair. There's other conformations for cyclohexane, but it involves pushing the electron clouds closer together. And then there's torsional strain, angle strain, all these different things. But yeah, so that's what we're talking about. We're talking about potential energy there. Do we get into wandering traveler? Do we get into other NMR like cozy spectra, cozy and nosy spectra? So that's very advanced. That would be studied in like a third year spectroscopy, exclusive spectroscopy course. So I won't talk about that here. We're doing organic chemistry 1, so we're not going to get any more complex than this very entry level NMR here. Yeah, okay, so yeah, that's good. So NMR is a big topic. It's one of the topics that students panic the most about with OChem. So just getting your feet wet, getting the basics down about chemical shift, integration, splitting, that is going to go a long way. Okay, so let's move on from NMR. Last time I said that we were going to dive into electrophilic aromatic substitution. This is another extremely important class, reaction class here. There are many different EAS reactions. And so we need to know them. Many of them are just kind of flashcard reactions. So you need to be able to do two things. You need to be able to look at the reaction conditions and know what is happening, what the transformation is. So for example, these are the conditions for nitration by electrophilic aromatic substitution. So what that means is you have an aromatic molecule like benzene being the classic aromatic molecule, and we're nitrating it. It means we're adding a nitro group to it. So NO2 is going to get on the ring. But here's the thing. We've got a hydroxyl group. This is a phenol. This is phenol. So if we have a hydroxyl on there, where does the NO2 go? Right? Because we're going to get, there are different structural isomers that are possible depending on the spatial relationship between the hydroxyl and the nitro group. So is there a preference? Is there any regioselectivity here? Is there regioselectivity? There absolutely is. And so we have to understand that some groups are ortho-para-directors and some groups are meta-directors. So hydroxyls are ortho-para-directors. So what does that mean? So here, this is the ipso position. The ipso position is the carbon that bears the group in question. So the ipso position bears the hydroxyl. Adjacent to that is ortho. Let me do this in red. So this is the ortho position. This is the meta position. And this is the para position. So an ortho-para director, a hydroxyl group, is an ortho-para director. It's going to direct any incoming electrophile to the ortho or para position. So we will get very, very little meta substitution. But the nitro group in this case is going to go, there's the hydroxyl. We're going to get some at the ortho, and we will get a mixture here. We're going to get a fair amount of both ortho and para substitution. This will probably dominate. The ortho will dominate simply because there are two ortho positions and only one para position. So purely statistically speaking, the number of collisions that occur, there will be more collisions occurring at the ortho position than the para position because there's two of them and there's only one para. Sterics are another factor, but here the hydroxyl does not provide a lot of steric hindrance. If it was a big bulky alkyl fragment, then you would start to see a dramatic shift towards the para product in the distribution. But here it's not. So this is going to be I don't know, 70-30, something like that. I'm not sure exactly what it is, but it's probably going to be more of the ortho than the para. So what did we have to do? We have to know this is EAS. We have to look at these conditions, nitric acid and sulfuric acid. We know those are the conditions for nitration, meaning we're adding a nitro group, NO2. And we have to know that hydroxyls are orthopara directors. So the orthopara director is going to direct the incoming electrophile to the ortho and or para position. Now, really quickly, one thing that we have to understand is that when we're looking at orthopara directors, we do not care what the incoming electrophile is. It does not matter that the incoming electrophile is a nitro group. It doesn't matter what kind of director the nitro group is. It's not doing any directing. It's the one that's being added to the ring. It is the group that is already on the molecule that is going to be providing the directing effect. The hydroxyl is already on the molecule. It is an orthopara director. It will direct the nitro group or any other electrophile to the ortho or para position. Okay, so that is one confusion I see a lot with students. So just to nip that in the bud right there. So now we have nitrobenzene. And these are the conditions for chlorination. So we're going to add a chloro group to the benzene ring. Where are we going to put it? We have to understand that the nitro group is a meta director. And so it will direct any incoming electrophile to the meta position. So here we're going to get almost exclusively meta substitution. So here's our nitro group that is still there. And we will get the chloro group at the meta position. So we just recognize that this is chlorination. We recognize that the nitro group is a meta director. So we go ahead and we chlorinate at the meta position. That's what we do. And so last one here, this is Friedel-Crafts alkylation. Friedel-Crafts alkylation. Stop it. Friedel-Crafts alkylation. So that's when we have an alkyl chloride and aluminum trichloride. Those are the conditions for Friedel-Crafts alkylation. So we're adding this alkyl fragment without the chlorine, right? So again, we have to understand what the reaction conditions mean, what we're attaching to the benzene ring. We're going to be attaching this ethyl group, not the chlorine atom. The chlorine atom will go away, but the ethyl group will be on there. And the iota group is a halogen. Halogens are orthopara directors. So let's go ahead and add the ethyl group to the ortho and also to the para position. And once again, probably the ortho substitution will dominate in the product mixture, or will be the main product because of the two ortho positions as opposed to one para position. But you will get a significant amount of both. So we say it's right. We say, right, there would be even a tiny amount of meta, but it's so insignificant that we don't count it as a major product. These are both major products, 70-30, whatever it is, something like that. Okay, so those are the basics. Well, the very basics would be unsubstituted, just on benzene. But then the second level is we have substituted benzene rings. All we have to do is we have to memorize which groups are orthopara directors and which groups are meta directors. If you forget, the rule is that groups that are electron donating will be orthopara directors. And the reason is that they stabilize the uranium ion intermediate when substitution takes place at the ortho or para positions, but not meta. So basically, the intermediate for the ortho and para substitution pathways is more stable than the intermediate for the meta pathways. So it dominates kinetically by a lot. So you get dramatically shifted towards orthopara substitution. So that would be something like a hydroxyl or an amino group, something that has a lone pair to donate by resonance. Also, alkyl groups. Alkyl groups are weakly orthopara directing because they don't have lone pairs, but they do hyperconjugation. So hyperconjugation is a weaker inductive effect that can stabilize the positively charged uranium ion intermediate. So those will also be orthopara directors, although more weakly orthopara directing than hydroxyl or amino. Electron withdrawing groups like NO2. So the reason that NO2 is withdrawing is because it looks like this. It's got a plus charge there and a minus charge there. So it's withdrawing because the nitrogen has a formal positive charge. So with the uranium ion intermediate, there's a resonance structure where one of the pi bonds gets pulled out of the ring onto the nitrogen and kicks the pi bond here up to get a second oxy anion. So if it's withdrawing electron density from an already unstable positively charged intermediate, that is going to be worse for orthopara. So basically, the meta directors make orthopara substitution less energetically viable, right? It makes the intermediate less stable, whereas that destabilizing effect does not occur through the meta substitution pathway. So meta will dominate there. So electron donating is activating. It happens faster and is orthopara directing. The electron withdrawing are deactivating. They make the reaction slower and are meta directing. The only exception is halogens, which are deactivating through the withdrawing effect from the polarity of the bond. The carbon halogen bond is withdrawing electron density, so it's destabilizing and slows it down. But because of the lone pairs, it is orthopara directing. So donating, activating, orthopara, withdrawing, deactivating, meta. But the exception is halogens, withdrawing, deactivating, but orthopara. That's all you have to memorize right there. So that's a little bit of EAS. Let's take a look if I missed anything. Excuse me. Looks like Pritam was following along. Jofi says, how do I know whether it's ortho or like para? So ortho-para directors, you will get a mixture of ortho and para substitution. Once again, there are reasons why one might dominate over the other. For example, if the directing group is a very large alkyl fragment, you might get almost exclusively para substitution. But just get used to the fact that in organic chemistry, a lot of the times you have a mixture of products. That's just how it goes. Tajwar says, did you cover RS configuration already, or will I cover it later? Yes, so I did do on like second, third, fourth week of this. We did all the chirality stuff. So Kahn-Ingold pre-log convention to assign RNS absolute configuration of stereocenters, E and Z of alkene configuration, enantiomers, diastereomers, all that stuff. So if you go to my live tab and go back to some of the first ones, the live streams I did for Chegg, you will see that content if you want to study those. Okay, I think we're almost caught up. Yeah, that's it. Okay, so that's EAS. Okay, a little more EAS, but let's do a related thing. So we can attach bromine atoms not just by bromination through electrophilic aromatic substitution, but we can also do radical halogenation on alkanes or cycloalkanes. So here, draw the starting material that would yield the desired product. All we need to understand here is that when you do bromination with UV light or heat, you're attaching a bromine atom to the most substituted carbon in the alkane or cycloalkane. So all this is this. Okay. So in the forward direction, all we did is if we do radical bromination, we're attaching a bromine atom to the most substituted carbon. Radical bromination is highly regioselective. So we'll get almost exclusively the tertiary alkyl bromide. So in other words, we're going to get the bromine there almost exclusively and almost nowhere else. Radical chlorination is a lot less discerning. The chlorine atom can end up almost anywhere on the molecule. And that has to do with comparing the stability of the chlorine radical and the bromine radical. The radicals are unstable for the same reasons that anions are. And so, if the bromide ion is more stable than the chloride ion, the bromine radical is also more stable than the chlorine radical. So that explains that. That was just kind of a random one in there. I just thought I'd throw that in. Maybe we'll look more closely at the mechanism next week, but that one is in there. Okay. Lesson notes. Danny says, what does HV and the triangle symbol mean? So the triangle symbol means heat, and HV means light. It's actually, so the energy of a photon is H Planck's constant times, it's actually nu. It's the Greek letter nu, but it looks like V, and sometimes we just say V. E equals HV. It's the frequency of the photon. So the energy of the photon is Planck's constant times the frequency of the photon. It's just a fancy way of saying light. And so the reason that we need either light or heat is that radical reactions always begin with homolysis. So just to give, I mean, we're not going to look at the whole mechanism here, but the way that it works is that normally when we do organic reactions, we're looking at heterolysis, where a covalent bond, the two electrons in that covalent bond go to one atom and not the other. But in homolysis, you got to have these single-headed arrows because they denote the movement of one electron, not two. A regular electron pushing arrow always denotes the movement of two electrons, a lone pair, a bond, whatever it is. But single-headed arrows denote the activity of a single electron. So that gives us two bromine radicals. So that's the initiation step. That's the initiation step of any radical reaction, is you have some compound that will undergo homolytic bond cleavage to generate radicals. Then the radicals propagate through other reactions, and then eventually there's termination, or there can be termination. So that's what HV and the triangle mean. And the reason is that particular photons of UV light will be what promotes that. The homolysis. It's either UV light or heat will promote homolysis. So that's how you get these radical reactions to start. Okay, let's move on here. Let's do a few more. So we want to devise a synthetic pathway for this target molecule starting from benzene. So we have two groups that we want to get on here. And we know that each of them can be attached to a benzene ring via electrophilic aromatic substitution, right? We know that we can nitrate benzene to get nitrobenzene. We know that we can do Friedel-Crafts alkylation to get ethylbenzene. So we're going to do a nitration and we're going to do a Friedel-Crafts alkylation. But what order are we going to do them in? It matters, right? Because these groups have directing behavior. Some of them are orthopara directors, some of them are meta directors. So we'll get different products depending on what order we do them in, right? So the nitro group is a meta director, and the ethyl group is an orthopara director. Now, what is the spatial relationship of the groups? They are meta to one another, right? This is right where they're two apart, right? Next to each other is ortho, two apart is meta, three apart is para. On opposite sides of the ring is para. So if they have a meta relationship, then it is clear that the meta director directed the other group to where it is, right? So what that means is if we do our big fat retrosynthetic arrows, this means back in time, not forward. We're saying what came before this. When you see this arrow, we're saying what came before this. So what came before this must be nitrobenzene, right? Because nitrobenzene is a meta director, so it directed the incoming alkyl fragment to the meta position. It can't be ethylbenzene because ethylbenzene is an orthopara director. So if we nitrated ethylbenzene, we would get the nitro group in the ortho or para position. That's not what we want. We're trying to get this one with a meta relationship. So we have to go back to nitrobenzene, and then from there we can go back to benzene. Right? Starting from benzene, we're good. Okay, so when you're doing synthetic pathways, It's good to do retrosynthetic analysis. This is obviously a very, very simple and very primitive example of retrosynthetic analysis, but it is synthetic analysis nonetheless. It is a good exercise in beginning to start to think retrosynthetically. We are thinking, what can I undo? What can I transform retroactively to get the thing that can have come before this? Because if I can undo some reaction to get the thing before this, and then again, and then again, and then again, until I get to some allowed starting material or some starting material that's very readily accessible from the stockroom. Then we have then all you have to do is play the movie in the other way, in the forward direction, and you have a synthetic pathway. You have a strategy. You have a strategy for the synthesis. So we did this retrosynthetically, and so now what are we going to do for it? Now we have to know what reagents we're going to use. So we said that we went from we got to go from benzene to nitrobenzene. So that's HNO3 H2SO4. That will give us nitrobenzene. And then we want to do Friedel-Crafts alkylation. That will give us the desired product, because the nitro group is a meta director. So we're only going to get the meta substitution on that second reaction there. So we had to know first of all what the conditions for nitrating and alkylating a benzene ring. Then we had to know the directing behavior. We had to know that the nitro group is a meta director and that the alkyl group is an orthopara director. Then we had to recognize that they have a meta relationship with one another. And then that was enough information to figure out what we're doing going backwards. We had to go back to nitrobenzene because the nitro group is the one that will direct the other group to the meta position. And then from there back to benzene. And then you just list the conditions going forward and you're all set. So that's these are good ones for introducing students to the concept of thinking retrosynthetically. What do I do? What came before this? And then what came before this? Sometimes it's very simple, like just pulling a functional group off the molecule. Sometimes it's more complicated, like unraveling a ring into a linear fragment or cyclizing something, or there's different you have to retrosynthetically cleave a carbon-carbon bond that was formed via Grignard or Wittig or whatever. But that's the introduction there. Let's see. Omar's question, please, Professor, is 1.8, 1.9 polar or non-polar? I think what you are asking is if the discrepancy in electronegativity between two elements is 1.8 or 1.9, will that result in a polar or non-polar? Well, actually, I think what you're asking is if it'll be polar, covalent, or ionic. That is a case-by-case basis. Non-polar caps off at around 0.4, 0.5 for electronegativity difference. 1.7 to 2 is kind of the gray area between polar, covalent, and ionic. That's case by case. You have to look at things like orbital mismatch, right? What's the relative size of the atoms? That's a factor. Let's see. Jofi, if the first is nitration, the second step is Friedel-Crafts alkylation. Right? This is Friedel-Crafts alkylation. Okay, let's do one more of these. Devise a synthetic pathway for this target molecule starting from benzene. So once again, this is exactly like the last one. So take just a minute and stare at this. This is just like the previous question, but with different functional groups. So what are we going to do? Once again, we know that these are two groups that can be attached to the molecule by electrophilic aromatic substitution. So what is the directing behavior of the groups? This is orthopara. And this is meta. So this one is, let me do that in pink. This is meta because it is electron withdrawing, because we have a carbonyl adjacent to the ring. So the carbonyl accepts accepts pi electrons by resonance, right? So in the intermediate, one of these pi bonds can go up here and push that pi bond up onto the oxygen. So that's electron withdrawing. So that means it's destabilizing and therefore meta-directing. So these are the two groups. This is orthopara and this is meta. What is their spatial relationship? They're para, right? So if they have a para relationship, that means that the chloro group must have directed the other group to the para position. It was not this group on there first, because that would have directed the chloro group to the meta position. It's not meta, it's para. So we got to do so the chloro group must be on there before this other group here. So we're going to go back in time with our retrosynthetic arrow to here and then to benzene. Okay, so it's not going to go back in time to with this group on there, because that would not give us the regiochemistry that we want. So now in the forward direction, we got to go from benzene to chlorobenzene. That's very easy. We're just going to do Cl2 in the iron trichloride catalyst. That will give us the chloro group there. And then we're going to do Friedel-Crafts acylation. So Friedel-Crafts acylation is this acyl chloride, again, aluminum trichloride catalyst, and that will give us a mixture of ortho and para, which we can then separate chromatographically. So this is what we wanted. We will also get some. Whoops, that's not a good benzene ring. We will get some ortho substitution, but we can separate that out by chromatography. So once again, we recognize that this group is orthopara directing. We recognize that this group is meta directing. We recognize that they have a para relationship. Therefore, it is the orthopara director that directed the other group to the para position. So we went back to chlorobenzene and then benzene. And then in the forward direction, we did chlorination on benzene, got our chlorobenzene, can go anywhere, it doesn't matter. And then we did the Friedel-Crafts acylation. All right, alkylation puts an alkyl group on there. Acylation puts an acyl group on there, both with the aluminum trichloride catalyst. Very similar mechanisms, and that gives us our dye-substituted product. So that's that one. Let's see what we missed. ENS, yeah. So alkylation and acylation, the only difference there is just the presence of this carbonyl, right? If you took this carbonyl off and you just had a chloropropane, one chloropropane, then it would be Friedel-Crafts alkylation. So definitely very similar mechanistically. What's happening on both? I don't have room to write out the whole mechanism, but whether you're doing alkylation or acylation, it's the chlorine atom on that fragment or on that molecule that is interacting with the aluminum atom on the catalyst, and then the electrons. What happens is that the electrons in the chlorine carbon bond leave and neutralize the chlorine. So you get, in the case of the alkylation, an alkyl cation. And then the alkyl cation is so unstable that a benzene ring will react with it, kind of like an addition reaction. Whereas the alkyl chloride is too stable for benzene to react, an alkyl cation that will react with benzene. And then similar here, the chlorine leaves, and we have a similar fragment just with the carbonyl there. So that's what that is. Whoops. Vectors, gym trainer. I'm in college Taking chem, do you recommend just memorizing OChem structures, or would you recommend trying to dig deep and understand the more fundamental nuanced moving parts? So I would heavily advise against just memorizing structures, right? Memorizing molecules won't do anything, right? What you have to understand is what's going on mechanistically, such that you can apply it to any substrate you are given. Definitely, when I was teaching, what I would see the most often is that students would memorize the example in the practice quiz or in the study guide, and they would just put that molecule on the quiz, which had nothing to do with the question, right? They would recognize what reaction it was, and they had memorized a molecule and put it in there. So no, you have to understand what transformation is occurring, right? When you do an elimination reaction, you get a pi bond in between the proton and the leaving group that are being eliminated, right? That's what you get. So if you understand that, you can apply that to any molecule you are given, to any substrate you are given. So it's about, yeah, you definitely want to go for the deeper comprehension such that you can apply it to whatever you are given. Anna Chowie says, Dave, can you actually synthesize these molecules easily in lab reliably with these processes, or is it a little more nuanced in reality? Obviously, it is harder than just drawing on a piece of paper. It's definitely harder and more nuanced than that. But yes, absolutely, this is stuff that you would do in an undergraduate laboratory course, right? In an OChem 2 lab, the lab component of your OChem 2 course, you would do, maybe not a Grignard because that's strictly anhydrous, but like a Grignard like. When I was an undergrad, we did a Grignard like thing, or you can do Wittig, you can do, you can do all kind. Yeah, most of the reactions that you learn, you do them, right? You carry out some kind of enolate chemistry or something like that. It's obviously, doing chemistry in the lab is not the easiest thing in the world, but you do it as an undergrad, so you just practice and you get better at it. Okay, we got time for one more real quick. So let's just do this one. Remember we introduced ozonolysis previously, so we're just going to keep bringing back little one-offs just to make sure we have all these in our bag of tricks, right? We don't want to forget any of these. So we're looking at these reaction conditions, right? We want to draw the product of the transformation. We look at this, we see ozone. You see ozone, we know we're doing ozonolysis, right? If you're studying organic chemistry, and you see ozone, we know we're doing ozonolysis. So what do we do when we do ozonolysis? Ozonolysis cleaves pi bonds, carbon-carbon double bonds, and the carbons that were participating in the double bond are now carbonyls. Okay, so we take these fragments and we're going to pull them apart. All right, and so what do we end up with? We have this 3-carbon fragment, and the carbon that was participating in the pi bond is now carbonyl. And then we have a cyclohexane moiety, and that is now a ketone as well. So here we had reductive workup, but it didn't end up mattering because when oxidative versus reductive workup only matters if you are deciding whether you are left with an aldehyde or a carboxylic acid. Here, these are both secondary carbons, right? For a secondary carbon, it doesn't matter because you're going to get a ketone either way, right? We're not going to break carbon-carbon bonds to heavily oxidize and get the carboxylic acid. So when the carbon's participating in the pi bond, well, not secondary actually. I mean, they're secondary after the fragments. Technically, they're tertiary because 3. But if we pull them apart, they would be secondary, right? And so you get ketones here. And so if they were primary, though, well, technically secondary, but like, for example, if this methyl wasn't there, if that methyl wasn't there, then we would figure out whether this carbon here that bears the carbonyl, would this be an H or an OH on that side? And that would depend on reductive versus oxidative workup. But here, it doesn't matter. We're good. We got our 2 products. We got acetone. We got cyclohexanone. And so that's ozonolysis. Cleave the pi bond, cleave the double bond, pull the fragments apart, stick carbonyls on those 2 carbons, the ones that were in the double bond. So that's ozonolysis. I had a few more here. Oh, so next is IR. We'll start there next week. Somebody asked for IR. So IR and NMR, and then sometimes you get questions with IR and NMR together. And so that's a good thing to learn about. So once again, go ahead and check out that QR code on the top left to see all of the different office hours that Chegg is offering through the semester. They got all kinds of subjects to help you with all of your classes. And of course, as you know, I will be here Tuesday at 5 p.m. Pacific time. Every Tuesday for the next, I don't know, 7 or 8, right, the rest of this semester, bringing you Organic Chemistry 1 review. Next week, we'll do a little more spectroscopy. I got a few other things planned. Maybe I'll throw in some of the earlier stuff just for people who maybe aren't as far along in the semester as this, right? I'm trying to kind of aim for something that will help everybody. So I'll keep diving back to the other stuff. But otherwise, thanks again for tuning in.